Hello, this is question 3 from the 2012 maths. So let f of x equal this function. What is this? This is a positive cubic with some unknown coefficients, a, b and c, that are real numbers. Figure below shows a section of the graph of y equals f of x. Curve has two distinct turning points. These are located at a and b as shown. Note that the axes have been omitted deliberately, which suggests we're going to be moving that line around. Find a condition on the coefficients ABC such that the curve has two distinct turning points, if and only if this condition is satisfied. Right, so two distinct turning points, we need two places where the gradient is 0. So let's differentiate 3x squared plus 2ax plus b. And we need two distinct solutions to that. So our b squared, which is 4a squared, minus 4ac, so minus 12b, has to be greater than 0. So, well, I suppose we could say a squared minus 3b has to be greater than 0. Right, a nice starter to get us going. It may be assumed from now on that the condition on the coefficients in that part of the question is satisfied. Okay. Let x1 and x2 denote the coordinates of a and b. So that's at x1, that is at x2. Okay, show that the difference between them is that. So the difference between those. So that's the two solutions of this. So for x1 then, x1 is going to be minus b, so that's minus 2a. We'll have to take off the square root to go to the lower value. X2 will be adding it on. So take off the square root of 4a squared minus 12b. Divide by 2a, which is 6. And we've still got all of those factors there, so we can take a whole load of 2's off. So x1 is going to be minus a minus the square root of a squared minus 3b divided by 3. x2 is then going to be that, but with a plus in the middle. So x2 is going to be minus a plus the square root of a squared minus 3b divided by 3. And now we need the difference, x2 minus x1. So we've got a minus a over 3 minus minus a over 3, so they'll cancel. Then we've got a plus of the square root over 3 minus a minus of it. So we're going to have two lots of that over 3 of the square root of a squared minus 3b, which is what they wanted. So far so good on this. Suppose now that the graph is translated as expected, so that the turning point of A now lies at the origin. Right, so we've got the origin is here. Let g of x be the cubic function such that y equals g of x has the translated graph. Show that g of x is that. So we need to show now what g of x is. Okay, so we know we've not stretched it in any way. So let's set up g of x of saying it's still going to be an x cubed. We haven't done any stretches, so we're still just going to have that bit from the translation, but these a's, b's and c's could have all changed. So let's say we've got dx squared plus ex plus f. Let's say it's that. So what do we know then? Well, we know that g of 0 is equal to 0. So that means that f is equal to 0. We also know that the gradient g dash of 0 is equal to 0. So that means that e is going to be equal to 0. So that's got rid of a lot of stuff. How do we get what d is? I mean, that's dealt with everything we know about a. We've only got b now. So we know that the gradient at b is also going to be equal to 0. So that is the gradient at b is x2 minus, that's why we worked out x2 minus x1. Okay, so g dash of 2/3 of the square root of a squared minus 3b, that is also equal to 0. Right, so we need g dash then. So that means g dash of x is 3x squared plus 2dx. We know that e and f are 0, so we can ignore all of that. So we'd have to plug that in. Right, this is going to be a squeeze. It's going to be a long line. So 3x squared. Right, when x is that, so we're going to have 3 multiplied by 4 over 9 multiplied by a squared minus 3b Then we've got 2dx, so plus 2 times d times x. That makes it look like dx, doesn't it? I probably shouldn't have picked a d there, but anyway. Then times 2 over 3, the square root of a squared minus 3b. That needs to be equal to 0. Right, so multiply everything by 3. That will get rid of that, that, and that. Divide by 4, we'll get rid of that, that, that. So we've got then, well, we can divide by this square root thing. So it's divide by that, which will make that a square root. So d is going to be minus the square root of a squared minus 3b. So we'll put a bracket at the end, take that along. So that's our d. So that makes g of x. Where's my g of x? It's this thing here. So that's now going to be x cubed minus x squared times the square root of a squared minus 3b. Is that what we've got? Yeah, they just factorised the x squared out the front. So, okay, that's fine. That was sneaky, but a bit of deductive work, and it comes together. I'm going to need a new sheet now. Let R be the area of the region enclosed by the x-axis and the graph y equals g of x. Right, so this was our origin at A, and then we want that region. So that's going to be R in here. So that's R. That is that region. Show that if A and B are rational, then R is also rational. Right, okay, so R is going to be, well, the integral from 0 up to some value here, whatever that is. We don't know what that is yet, do we? Oh, well, it's easy enough to see because the other root is going to be this when x is the square root of a squared minus 3b. Right, so R then is going to be the integral from 0 to the square root of a squared minus 3b of g of x, which is x cubed minus x squared, the square root of a squared minus 3b, dx. Okay, so x to the 4 over 4, that's the first one. And then we're going to have an x cubed over 3 multiplied by that square root of a squared minus 3b. And that is between 0 and the square root of a squared minus 3b. Well, at least the 0 we don't have to worry about. So that R then, so we've got that thing to the power of 4, which then becomes a squared minus 3b all squared, divided by 4. And then we've got that thing to the power of 3, and then multiplied by it again. So we've also got a squared minus 3b all squared, divided by 3. So that then is, well, quarter minus a third is minus a 12th of a squared minus 3b all squared. So what were we trying to show? If A and B are rational, then R is also rational. Well, yeah, there we go. I mean, it's just straight there, isn't it? There's nothing irrational about any of this. We've got rational squared minus a rational is going to give us a rational. So that certainly works. So you'd have to actually write out the line. I'm just trying to save a little bit of space on the screen for the last part of the question, but you'd have to write out. Therefore, if A and B are rational, R is also rational. Is it possible for R to be non-zero and rational when A and B are both irrational? Well, there's a question. Justify your answer. So R to be non-zero and rational when A and B are both irrational. So we'd need a to the 4 minus 6ba squared plus 9b squared to be rational. So we need that to be rational. So that means, so b would have to be a square root. So we've got b is some square root of something, and of x, and a would be a fourth root of something. So if we add that, then what do we get in the middle? We'd get a 6 lots of a square root times a square root. So yeah, that would work, wouldn't it? Yeah, so we'd have to write that out in a different way because we don't have to have it for all cases. Is it possible? So we just need a possible solution for this. So we could say let a equal the fourth root of x and b equal the square root of x, then we could put all of that in and say we'd get the fourth root of x to the power of 4 minus 6 lots of the square root of x times the fourth root of x squared plus 9 of the square root of x squared. So you can then simplify that and say, well, that is x minus, what have we got? Oh yeah, that's the one that just comes out as 6, isn't it? Because you've got the square root of x times the square root of x times 6. So minus 6x plus 9x, which is, whatever that is, 4x, which is rational for a rational x. So so we'd have to have that and rational x. So you could, I suppose you could pick a single number. You could just say for 2. So we could have done this again and said, okay, we've got the fourth root of 2 to the power of 4 minus 6 times the square root of 2 times the square root of 2 squared plus 9 times the square root of 2 squared, and then show that that is a rational number because you get 2 minus 12 plus 18, which gives us 8, which is the same as we've got there. So there's two different ways because you don't have to show all cases or anything. You can just do there's a justification for your answer. It is possible. We've managed to show a case where it works. But yeah, we're guided by these things. If that is going to be irrational a, then you have to take it to a fourth power or some other multiple of 4 in order to get rid of that. And then similarly, if we got an irrational b, you need to take it up to a squared or some other higher power to get rid of that irrationality. I'd say that was a pretty tough question. I mean, it went through sort of okay, but there was a lot of keeping track of what was going on. But I suppose really maybe it hinged on the third part, if you could do the deductive work of setting where the origin is. But it does give the option. Maybe that is why they gave that solution here to part 3, because if you didn't manage to get that part there for part 3, then parts 4 and 5 were still open to you off of the back of it. So maybe the third part was the hardest part of it. But yeah, that was a challenging question, that one.